Hey guys, this is Joseph, one of your TAs for Intro to Deep Learning. Today I'll be giving Recitation 0B on vectors, tensors, and the index notation in NumPy. If some of the math here seems unfamiliar, then there's a good resource by Dr. Kelly on these three topics. The goal of this notebook is to help you understand how to write different mathematical objects in NumPy. So we will be covering setting up NumPy, vector arrays, matrix array notation, and tensor arrays. Jumping right into it, we'll start with setting up NumPy. We install NumPy using pip, similar to how we would install any other library. And the command is given here. And to find this command in addition to alternative methods, you can go to the URL here. We also import the NumPy library similar to how we'd import other Python libraries. We import NumPy as NP, where NP is the standard alias for NumPy. I'll also set a random seed, so when I generate random numbers later on, you'll see similar results if you're following locally. Next, we'll start with vector arrays. I'm going to assume that if you're taking Intro to Deep Learning, that you have some experience with linear algebra. This will be a little bit of review, but the main purpose of this recitation is to show how the math translates to the code. So consider the following three coordinate vector arrays, E1, E2, and E3. You can think of these three as representing the x, y, and z axes. Each of the coordinate vector arrays, like the axes they're on, are all at 90-degree angles to each other, where none of them is a scalar multiple of the others. In the code, we see that you can declare a vector array by calling np.array and passing a list with the respective components of the array. When we print this, we see that we get what we expect. The dot product between two vector arrays is defined as the product of their magnitudes times the cosine of the angle between them. So, in the case of the coordinate vector arrays, we know that the angle between any two different coordinate vectors is 90. Since the cosine of 90 is 0, we see that the dot product between the two is 0. In NumPy, we use np.dot to calculate the dot product between two vectors. If we print the dot product of these examples, we see that we get results that we expect. Then, if we look at the vector arrays that are the same, we have the angle between them equal to 0. In the example of coordinate vector arrays that are the same, their magnitude evaluates to 1, and their cosine of 0 evaluates to 1, so their dot product evaluates to 1. Looking at the code, we see that their dot product evaluates to 1, just like we'd expect. We often want to look at scalar multiples of the coordinate vector arrays. For example, if we have a scalar a1 equal to 3 and coordinate vector array e1, then we would write their product as follows. Scaling the e1 coordinate vector by 3 yields 3 in the first vector array component. For a more complex example, consider scalars a1, a2, and a3. If we scale the coordinate vector arrays e1, e2, and e3 by their respective scalars, then we write the vector array A, defined by the sum of the scaled vector arrays. Scaling e1 by 3 gives 3 in the first component. Scaling e2 by 1 doesn't change the vector. And scaling e3 by 4 gives us 4. Adding the vectors up, we get an A of 3, 1, 4. In the code, we can define the respective scalars and then scale the coordinate vectors by these amounts. Taking the sum of the scaled coordinates, we get a result similar to what we expect. We can also write the sum of scaled coordinates in summation notation. Here, we have the sum from I equals 1 to 3 of AI, EI. So in the code, we have a list of components A1, A2, A3 that correspond to a list of coordinate vector arrays E1, E2, E3. Then, for each component index, we can first define a 0th placeholder. Then, for each index I of the components and vectors, we can accumulate the product of the two. That gives us a result like we got earlier. We could also use the zip function to create an iterable object, where each iteration increments the corresponding index of the components and vectors. We call the component and vector here, and this loop gives the same result as the previous loop. After combining different scalings of different coordinate vector arrays, we are able to create coordinate vectors that carry information in multiple components. If we want to take the dot product of these more general vector arrays, then we can derive a general form you probably know. The dot product of u and v can be rewritten with respect to their coordinate vector scalings. If we multiply it out, we get more verbosely this equation here. Like we saw at the beginning, the coordinate vector arrays that are the same have a dot product of 1, and their coefficients are preserved, while the ones that are different have a dot product of 0, and their terms are dropped out. This allows us to write the dot product of u and v in a more familiar form. In the example where u equals 314 and v equals 159, then the dot product of the two vectors u and v can be written as the product of their respective components, which in this case evaluates to 44. In the code, there are a few ways to do this. The first uses a list of the u components and a list of the v components. If we divide the vectors u and v as the sum of the scaled coordinate vectors, then we can directly calculate the dot product of the two vectors and get 44. We get the same result if we use for loops, writing out verbosely the dot product calculation and accumulating the product of the coefficients and the coordinate vectors involved. We still get 44. We can also directly calculate these coordinate vector arrays and directly calculate the result. We get an answer of 44. Since we can see that only the indices that are the same are used, we can simplify the for loop. We write the dot product as the sum of the product between scalar components. In the code, we loop over each component index and accumulate the result. We still get 44. And using the vector arrays created directly, we can directly calculate the result using np dot, avoiding the need for for loops and arriving at the same calculation of 44. A more formal way of writing when indices are the same, yielding unity, is with Kronecker delta, which is defined as 0 if the indices are different, and 1 if the indices are the same. This is equivalent to looking at the dot product of the coordinate vector arrays with respect to their index, because if the indices are different, you get 0, and if they're the same, you get 1. Comparing all the different cases for our example, we see that they are in fact the same. Next, we go to matrix array notation. Here, we'll start with an example of a 3x1 matrix array, V. Its transpose can be seen here as being a 1x3 matrix array. To fill this array with random numbers from a uniform random distribution, we can use np.random.random. In the code, we simply declare the variable and transpose the array using .t. We will also want to look at the transpose of 3x1 matrix arrays, such as the example of U, and we can similarly transpose like we did before. In matrix array multiplication, for each row of the left matrix and each column of the right matrix, we look at the sum of the product of their corresponding coefficients. In the code, taking the dot product of the transpose of U together with V gives us the following result. The identity matrix should also be familiar, and we can create it in the code using np.i. Whether you are using chronic or delta to refer to individual elements, the identity matrix to refer to the entire object, or writing out exactly what the matrices and vectors contain, these are all the same. Here's an example of matrix array multiplication between a 3x1 matrix array and a 1x3 matrix array. For each row and for each column, the corresponding coefficients are multiplied, yielding a 3x3 matrix array. In the code, we multiplied the two matrices using np.matmul, and we see the 3x3 result we expected. When converting the 2D matrix arrays to 1D vectors, we can calculate the tensor product to give the same result. The tensor product of two 1D vectors is calculated such that the vector on the right is scaled by the corresponding coefficients of the vector on the left. A new dimension is created with each index corresponding to the values given by these respective scalings. These second and third lines are equivalent. In the code, we can convert the 2D matrices into 1D vectors by using the squeeze function. Running the code, we can see that the tensor array product of the vectors gives the same result as the matrix multiplication of the 3x1 and 1x3 matrices. Next, here's an example of matrix array multiplication between a 3x3 matrix array and a 3x1 matrix array. For each row of the matrix on the left, the row coefficients are multiplied by their corresponding column coefficients of the matrix on the right. Each index of the resulting matrix is the sum of the product of these scalar pairs. This result is not equivalent to the tensor array product between a matrix and a vector because the matrix on the right is not scaled by the corresponding matrix on the left, and a higher dimensional object is not created. Just for completeness, we'll also look at the transpose rule here. The transpose of the quantity of two matrices multiplied is equivalent to the respective matrices swapped, transposed, then multiplied. In the code, we show how to write these expressions, and we see that the two are equivalent in this example. Moving on to tensor arrays. Before, we saw the tensor product of two 1D vectors is calculated such that each vector on the right is scaled by the corresponding coefficients of the vector on the left. Now, consider this vector array with 3 components and this 4x4 matrix array. Here, we will look at the tensor product of a 1D vector array and a 2D matrix array. Similarly, a new dimension is created with each index of the new dimension corresponding to the values given by the respective scalings. In this example, our result is a tensor array with 3 dimensions. I'm going to write this out a bit differently to save space. using commas to separate indices of this third dimension. And just for the sake of visualization, I'll call each of these components tau and subscript them with their corresponding index for each of these three dimensions. Visualizing the tensor, we see that the first dimension corresponds to what we will call a record, the second dimension corresponds to a row, and the third dimension corresponds to a column. One of the things we might be interested in is deducing the relative scalings given such data, in addition to more complex relationships. In the code, we see that given a 1D array and a 2D array, the tensor array product of the two yields a 3D array. In practice, we do not get the data in such a nice form. The records may be gathered differently, or may be corrupted and lose information. But we still want to learn how they relate to each other in terms of their relative scalings, so we need to convert the messy object into a more manageable object. Taking a closer look at our example here, we have a list of records that are each 2D. Record 0 is red, record 1 is green, and record 2 is blue. Our goal is to make these records have similar dimensions so they can be represented with a tensor. There are a few ways we can do this. One option is to subset or slice each of the records such that there is consistency between them. Here, we can subset at most 2 rows and still have consistency, since you cannot subset more than 2 rows from the green record. Another option is to supplement the data by padding or adding additional rows. To get consistency by padding, we might add rows with zeros until they all have 4 rows. This is because the blue record has 4 rows, and this is the most number of rows between the 3 records. The first option could be preferred if it does not make sense to add additional data to the object, while the second might be preferred if we can make sense of a padding that doesn't compromise the existing information. In our first example, we'll see how to subset the first 2 elements to make a tensor array. There are different ways you can choose to do this, but here we'll use a list comprehension and familiar Pythonic indexing. For each record, we subset up to index 2 and return a list of the result. We then convert the list to an array, and we can see that the result is a 3D object. In our second example, we'll see how to subset the last 2 elements to make a tensor array. We use similar Python syntax to what we did before. The negative allows us to start at the index 2 steps back from the end. We select up until the end, so this gives us the last 2 rows. Converting to an array, we see that we get a similar 3D shape with the new values. Next, we're going to look at padding, which is similar conceptually in terms of its complexity, but takes a little getting used to in the code. We need to specify where and how much we want to pad the array in the np.pad function. In this example, we're going to pad the end of the array with zeros until they're the same size of 4. We start by specifying how much we want to pad the end of the array. We also need to specify how much we want to pad the other sides, but in this case, we don't want to add any additional padding. After we identified how we want to pad each array, we need to specify it using the following syntax, using a tuple of how to pad the beginning and ending of the dimension with one tuple for each dimension. There are 3 specifications here, because there are 3 records. When it comes to using the np.pad function, we first pass the record, then we pass the specification, then we identify how much we pad the array with the mode, and then we specify any other details required for that given mode. Here, we want to do a 0 padding, so we specify a constant value of 0. We apply np.pad for each record given their respective specifications. Then we convert the result to an array. Printing the result, we can see that we created a new array that is a 3D object, which each have the same size as the largest record. In a slightly different example, we might want to pad above the record. Here, we simply change our specification for what we would like to pad above. We want to apply np.pad for each record and specification, then convert the result. We get a similar shape as before, but the padding is on the top instead of on the bottom. Finally, sometimes we don't want to go through the work of slicing and padding, and we can get away with simply creating a lower dimensional object. For things that are sequential, this might make it harder to tell how the rows relate to each other, but this can be a quick solution that retains most of the information. And that's it for this recitation. Please feel free to comment or ask for clarification in the comments or posting on Piazza.